Okay, welcome to Sundar's lecture. This is lecture number 2 actually. So let us we see what are all the topics we have covered in the last class. In the last class, we have taken resistors, and in resistors, we have seen that resistors are memoryless elements, and if you want to find what is the instant value of current, we don't need the past histories of voltages, right? So this is the content we have seen in the last class, right? So in this class, this is lecture number lecture number 2, right? So in this lecture, we will see inductors. In the last class, we have seen resistors. Now we will see inductors. Right? For that, I will take a circuit again. I will take a circuit. An inductor is connected across the voltages. I am drawing a different circuit. I will explain you why I am drawing like this. So this is the inductor. So inductor, here I have connected a switch. This is position A and this is position B, right? And this is voltage supplied V, and this is the inductor. And current flowing through this inductor will be I. I am taking it as I. And a circuit where I can draw like this, right? So first, if you want to understand what is inductor, right? Uh, Inductor, by Faraday's law of electromagnetic induction, what is the voltage across the inductor? That we can easily find if you take Faraday's law of electromagnetic induction. By Faraday's law of electromagnetic induction, by Faraday's law of electromagnetic induction, what is the voltage across the inductor? The voltage across the inductor will be V across the inductor will be equal to L di by dt. That we know already, right? If you want to know this, how this expression is coming, you just go through the basics of inductors, that the voltage across the inductors by Faraday's law of electromagnetic induction. Fine. Now, fine. Now, what we will do, we will connect this switch to position number A, right? So, at position, switch at position A, right? Now, this circuit will be connected, that this inductor will be connected across the voltage source, right? And what is the voltage across this inductor? Now, the voltage across this inductor will be L into di by dt. That is what we have written here, right? That is what we have written here, right? Now, uh, what I am going to do, I am going to find what is the current, right? I need to find what is current, right? So what I am doing, this is expression number 1. From this expression number 1, I am just going to get the I expression, right? So for that, I will keep di by dt one side will be equal to VL divided by L, right? So you see here, what I can do now, this dt can be bring to the right hand side. So VL by L into dt. So I can write the expression like this. So if I integrate on both sides, integrate on both sides. So integrate on both sides, this integration will be di will be equal to 1 by L integration of VL into dt. So you see here, if you apply Kirchhoff's current voltage law in this loop, this is one loop. If you apply in this loop, you see here it is L into di by dt, that is the voltage across inductor, and this is voltage, right? V. So here by Kirchhoff's voltage law, we can write by KVL, by Kirchhoff's voltage law. So if you want to write the KVL, you start from here and you end here. So what it will be? So if you are going in this direction, because my current is in this direction, so you go from here. So you are crossing from minus to plus. So this will become plus B, and you are going in this direction through the current. So this, if this is the inductor, so obviously this will be plus and this will be minus, because inductors will always absorb, right? Absorb the energy here, absorbs energy. So what, the symbol becomes plus here, minus here. So you are traveling from plus to minus, and what is the voltage value? L into di by dt. So that will be minus L into di by dt will be, that's all, right? Nothing else is connected across, connected after this inductor. So this becomes equal to 0. So V will be equal to L into di by dt. And what is this L di by dt? So that is nothing but V is equal to VL. That's all, right? So V is equal to VL. So this is expression number 2. So from 2, you can write what? So integration of di, it will be I, it will be I will be equal to 1 by L integration of V into dt. That's all. So this is the final current expression here in this loop. This loop current becomes I is equal to 1 by L integration of V dt. And uh, what is the limit of this integration? This limit will be equal to what? Minus infinity to, uh, what is the time you need to find, right? So if you want to find what is the current value, so for example, you take that this circuit is connected at a particular time, at a particular time. Now I need to find what is the current at 5 seconds. Again, we will take the same thing at a particular time. So what I will do, I will write I is equal to 1 by L integration of, so I, let us consider that this inductor has not been connected to any voltage source before that particular time. So I will take this is 0 to particular time t into V dt. Now what I need to find? I need to find what is the current at 5 seconds, right? What is the current at 5 seconds? So I need to find current at 5 seconds will be equal to 1 by L integration of 0 to 5 into V dt, right? So you see, now for our convenience, let us consider the inductor value and the voltage value. So let us we consider V is equal to 5 volt and inductor is equal to 1 Henry, right? V is equal to 5 volt and inductor is equal to 1 Henry. And now you see here, you substitute these values here. So I at 5 seconds will be equal to 1 by 1 integration of 0 to 5. What is the V value here? V is 5 into dt. So if you simplify this expression, I of 5 will be equal to, so 1 by 1 becomes 1, and this term becomes integration of 5 into dt. This is actually constant value. So if you integrate with respect to t, so it becomes 5t into, and the limits of the integration is 0 to 5, and this becomes I at 5 seconds will be equal to 5 into 5 minus 5 upon 0. So this So I'm just substituting the upper limits and lower limits in this expression, and here you see this becomes I of 5 will be equal to 25, right? This becomes 0, 5 of 0 becomes 0, and this is the final expression for the inductor current, right? So I at 5 seconds becomes 25 amperes. I at 5 seconds become 25 amperes, right? Now what I really want to tell you here, you just try to find what is I at 6 seconds now. 6 seconds, right? So if you want to find I at 6 seconds, go to this expression again. Go to this expression again and you substitute I at 6 seconds. So one by one, I'm just directly substituting the values of inductors. So this becomes 0 to 6 and this becomes 5 into dt, right? So what it will come here, this becomes again 1. So this expression, if you integrate 5, it becomes 5t. The limits will be 0 to 6. So I at 6 seconds will be equal to 5 into 6 minus 5 into 0. So this will be like this. So here it becomes 30 amperes. So 30 amperes. So I at 6 seconds becomes 30 amperes, right? So now you see I at 5 seconds it is 25 amperes. I at 6 seconds it becomes 30 amperes. And if you substitute and if you find what is I at 7 seconds, it becomes 5 into 7, that is nothing but it will be 35 amperes. And if you want to find what is I at 8 seconds, it becomes 5 into 8, that becomes 40 amperes, right? Now you see, it is, you have to understand very clearly here. So if I apply a constant voltage, that is DC voltage, to the inductor, this, the current in the inductor is increasing with time. It is increasing with time, right? So I just want to draw a graph. I just want to draw a graph. So if this is current I in the inductor and this is time, right? So what happens here? The current is increasing with respect to time. And what is the limit of this current? Since you can, let us consider this inductor, rated current is 5 amperes, sorry, 25 amperes. And you see, if the rated current is 25 amperes, you cannot supply the voltage beyond this 5 seconds, right? That is the point you need to understand. And if you apply beyond 5 seconds, it becomes 30 amperes. So that this inductor will be busted, right? That is the point you need to understand, right? Now what I am going to do, that you see here, at 5 seconds, the switch will be connected to position B, right? The switch will be connected to position B. And what happens here, you see, if switch is connected to position B, then this inductor, which is nothing but we are just short circuiting the inductor. And what happens if we short circuit this inductor, that we will see with this continuation of the course, with the continuation of this lecture. Fine. If inductor is short circuited, then what happens? This VL or this V becomes 0. And if this V becomes 0, it is very interesting that di by dt also becomes 0. Which means that the current in the inductor is not going to change. That I will explain. Okay. Now we will take to the next page. So what happens if this inductor is connected to, the switch is connected to position B, right? So we will take to the next page, and I'm just drawing the diagram. So now you see this inductor is connected like this, right? So this is the inductor, and current flowing through the inductor is I, and now it becomes like this. So what happens here? VL becomes what? 0. Since it is short circuited, the VL becomes 0. So if VL becomes 0, and you see in the previous previous page, you see V is equal to VL, right? So if V is equal to VL, now here V will be equal to 0, that is nothing but will be equal to VL. Now you see, you take this expression, you see here this expression, you take expression number 1, that means VL is equal to L into di by dt, and all these things are happening when, that is, you have to understand it clearly. At 5 seconds, exactly at 5 seconds, I'm just switching this position of the switch to B, position B, right? And what is the current flowing at that time? At that time, the current flowing through the inductor is 25 amperes. That is also you have to understand, right? So I will write here, at 5 seconds I am doing these things, right? At 5 seconds, what is the inductor current? Inductor current, which is nothing but it is 25 amperes. That is also you have to understand very clearly, right? So at 5 seconds, I have short circuited the inductor, and the voltage across the inductor becomes 0, and the expression, this expression, you take this expression, VL becomes 0, which is equal to L into di by dt, and if this L comes to the left hand side, that also becomes 0, and what finally we are getting, the expression di by dt is equal to 0. And what is the thing you have to understand? If di by dt equal to 0, this expression explains that there is no change in current. So you see, di by dt, change in current becomes 0. There is no change in current in the inductor. There is no change in current in the inductor. This is very important. Now you see, at 5 seconds, inductor current is 25 amperes, and we are getting that there is no change in current after that. So that what happens here, the inductor will carry 25 amperes forever. This inductor will carry now 25 amperes forever. That is the point. It is very important point, right? So now what is the inductor current? So inductor has 25 amperes of current, and from this content we can literally say that inductor can store energy, right? Obviously it is storing, right? Because I have connected a voltage source across inductor, and the current through the inductor is increasing linearly. That I have seen in the uh, last page. In the last page, you can see here, if I is after 5 seconds it is 25 amperes, at 6 seconds it becomes 30 amperes, at 7 seconds it becomes 35 amperes. So it is increasing linearly. So what I have told you, so after 5 seconds you should stop the increase of current in the inductor. Why? Because the rated current of this inductor is 25 amperes for me. I have considered this inductor will carry up to 25 amperes, right? So you have to stop at 25 amperes, and what I am doing there, I'm not removing this voltage source. Instead, I have short circuited this inductor. If I short circuit this inductor at 5 seconds and it becomes, there is no change in current. I am getting the expression as there is no change in current. So at 5 seconds, whatever the current passed through the inductor will be stored. Will be stored. It is very interesting, right? You see, 25 amperes of current will be there in the inductor forever. And that is the point you need to understand. And if you connect this inductor across any resistor, now from this point, it will deliver the 25 amperes to the resistor. So you have to understand that inductors can store energy by this point. But I have not given the expression how much of energy that this inductor can store it. That we will derive the expression for that. What is the expression for the energy stored in the inductors? That we will see with the continuation. Anyhow, the point you have to understand that inductors can store energy literally, but we have not fully uh, found what is the expression for the energy storage in inductor. Fine. So with this, we will stop in this lecture. And in the next lecture, I am going to derive the expression for how much of energy that this inductor can store. We will express it. Fine. You go through this, and if you have any doubts, please ask me in the comment box so that I can also learn from you people. Right? Thank you.